To introduce ourselves again, we are the Geological Society of the Oregon Country. We're the oldest collaboration of amateurs and professional geologists in the Pacific Northwest. We've been around for 85 years, doing field trips almost every year, except for this year, and monthly lectures at Kramer Hall at Portland State, who have been our gracious hosts for the past 50 years almost. And Scott Burns is Scott and Sheila are both professors there. And so we're happy to have them and their connection, and also our connection to other professional geologists really makes a big difference. One of the things about this meetup is anyone can come in as an amateur, as someone who just knows a little bit about geology or a lot about geology, and get into a conversation with Dr. Burns or Sheila or many of the other people here. And so I would encourage you to ask questions, especially the stupid ones, like what's the difference between a rock and a mineral? What's a feldspar? What is plate tectonics again? Those questions that you feel when people start off on a topic and you think like, oh, I don't want to ask that because everyone seems to know it. That's when we'd like you to jump in. Normally we say, well, put your questions in the chat. And I think Carol Miles, if you're out there, you're going to monitor the chat for us.
Yeah, I'll go ahead and do that.
So do that if you're shy or if you don't feel like you want to interrupt the speaker. But with this number of people, and we're at 25, and I think that's about perfect, feel free to just unmute yourself and interrupt. I think it's a small enough group that you can do that. And I would rather have that happen and have the question, get into the conversation than sort of wait. And again, ask those questions that are the stupid ones. I get 2 or 3 occur to me every time, and I often don't ask them because I'm embarrassed, but that's how we get the conversation going. A little bit about the club and what's coming up. We have our next lecture, and Sheila, could you describe that? Or we don't have Denny here, our normal program director, but who is our next speaker?
Our next speaker is going to be Dave Taylor, who is a geologist, and he is going to talk about the first dinosaur fossil that was found in Oregon. Now, you might not think that dinosaurs, we don't have a history of having dinosaurs here because largely Oregon didn't exist during the time of the dinosaurs, and yet this one was found, and so Dave is going to talk about that.
Wonderful. Do we have any other events coming up at this point? I know we will have our monthly lectures going forward, and as Carol mentioned earlier, field trips hopefully will be rescheduled starting in the spring. Am I missing any other things that are coming up? Any other announcements? And then we're going to talk about Dogami. Okay, well, if anyone can think of any other GSOC announcements, let me know. But let's talk about the the Oregon Department of Geology and Mineral Industries, or Dogami. And I think Clark and Sheila and Scott, maybe you can give us the report there. Whoever wants to jump in, maybe Scott.
Scott, we're waiting to hear from you.
I'll take the lead, and if you guys don't realize, Clark worked for Dogami for quite some time too, and is retired from there. But we found out recently that the governor's budget that has been presented to the legislature basically is eliminating Dogami, our state geological survey. And almost every one of the states in the United States has a state geologist and a state geological survey. The State Geological Survey controls all the mines, if there are any mines that are in it. Number 2, they put together geological maps and the geological history of the state. And number 3, they deal with all the hazards. And so on the West Coast, we have them all. We have earthquake hazards, flood hazards, landslide hazards, coastal hazards, tsunamis, volcanic hazards, everything. I've had a chance to work with probably 10 different geological surveys across the United States. And I think we have one of the best, and one of the best bang for the buck. What we as Oregonians get out of it for the amount of money that the state puts into it is incredible. They have been working very, very hard, especially in the last 20 to 30 years, talking about earthquake hazards, flood hazards, and landslide hazards. We are the leading state in the United States in the production of landslide hazard maps with susceptibility maps, hazard risk maps, and then inventory maps. And other states are now adopting all of our things that we've done here. Also, a lot of our earthquake stuff. In the governor's budget, starting, we're in a biennial budget starting in July. There are 39 positions in Dogami. 11 of them are down in Albany. They are related to mining. It is a neutral thing. The amount of money coming in equals the salaries of the people there, and so and that's from the mining. All the mining companies have to be registered. But the other, so there are a total of 39 positions in Dogami. And so that's 28 that are here in Portland, and then also on the coast in eastern Oregon. And basically, she's eliminating those. And the 11 people, so in the first year of the budget, 21 through 22, there will be a significant reduction in the amount of money for them. And then at the end of July of 2022, the 11 people in the mining area will go over into Department of Environmental Quality, and they will be a separate group within the DEQ. And then the other ones, the 28 positions, will be reduced down to 6 or 7. And they will be absorbed in land conservation. The name Dogami will have disappeared. The website will have disappeared. What will happen to the state geologist, we don't know. And all of the consultants here in Oregon rely on the websites for the LIDAR and landslides and everything like that. There will be of the 6 people or 7 remaining people in Dogami that will go into land conservation. One will be a grant manager, one will be a graphics person, so there'll be 5 geologists, and that's it. And so, so we are asking people to write to their legislators. Everybody in Oregon has got a senator and a representative, and asking them to, because the governor's budget then is massaged during the whole session, and then it comes out at the end. And save Dogami. Basically, it's $3 million. That's it that is out there, because they get $4 million every year from the feds, because they do an awful lot of contract work. And from the state, and then again, Albany is another thing. So it's only $3 million. So we're saying, please save Dogami, keep it as is, and because they do an awful lot for the state of Oregon and the industry. I mean, in our profession. And
Scott, what can we do?
I think that everybody should write letters to the editor, not until after Christmas, but and that's awareness. But then also write to the legislatures and the legislators who are on the Ways and Means Committee at the legislature. They're the ones that make up the final budget. So what I'm going to do is figure out who the members are of the Ways and Means, and then my legislator, my representative and senator write to them.
So Patty has a question which is in the chat, but I know you're very shy, Patty, but maybe you can unmute and you can ask your question.
I can unmute. No, I was just thinking it'd be easier on me if I had a template letter to work off of and maybe a list of who all to send it to.
Well, I know as GSOC, we definitely support saving Dogami. And so we are going to mount an effort that we can do through GSOC. I can put together a template letter with the help of Scott and Clark, and you know, just to make sure I get it straight. We can do something like that. So, you know, we can do it as an organization, but individual, the more letters they get, the better from individuals. So,
all right.
Yeah, I'll put
So
that on my to-do list.
I would like to make a comment that my other main interest these days is climate change, and DEQ is really busy right now in all of the things that they have to be doing under the executive order to reduce greenhouse gas emissions. And it seems unlikely that moving most of this over there would be a very good idea at this time. So I'm going to put that in my letter. I don't know.
That's an excellent point, Kathy.
Because I have been monitoring the DEQ activities for the League of Women Voters.
Right.
I have a question too in the chat.
Eric, go ahead.
Where are they proposing, which department will be taking over the hazards concerns?
That will be in land conservation and development. There'll be 5 desks that'll be there.
5 desks for a state that is anticipating a big earthquake.
I agree.
So it sounds
Yeah,
like
I
we
had
will
a-
have something on our website about maybe a template letter and then information that'll go out to our members. It's a conversation we'll probably have in the next meetup. So if you're not a GSOC member, stay tuned and we'll be continuing to have the conversation. Anything else? Go ahead.
Think if you could let us know how much synergy there is by having all of these people in the same department that they would lose by having them split up into a whole lot of other departments. I think that would be a good thing to put in our letters if we want to say we want to keep them together, not just
Right.
we want to keep the people involved, but we want to keep it as a unified organization.
Kathy, you make a good point about the synergy with other issues, especially climate change and environmental justice. And I know Kathy and I have been on another committee together. If there are other ideas that you have about that, please.
Well, I was specifically talking about having all the geologists being able to be synergistic with each other.
Yes, right. Okay. Well, thank you, Scott and Clark and Sheila, for keeping our focus on that issue. Miss Tater, I'm sorry, Tater. If you want to unmute real quickly, you got a really good question that maybe you can ask later about the lists. Any other announcements before we head into the proper geology news? Oh, there's Tater. Okay, he's waving. I hate to
I'm not
miss
sure
any.
if my audio is working correctly. It cuts out a lot. So
You've got a little flutter in your woofer or something, but we are hearing you.
I'll have to work on it a little.
Little
Anyway,
echo.
my short intro, I'm from Portland, and I go around and look for rocks, for years now. And I have all kinds of stuff sitting around the place. I don't know if you can see that mosaic. But anyways, I'd like to get a little bit more of the bigger picture now. So I'm checking out groups like this. And
That's
especially like I said in the comments, I was camping along the John Day River in Sherman County this summer, and just noticed I think the landscape's really unique there, really. And I asked somebody, what makes this the way it is? And they said, well, there's just no trees. That's what the land looks like when there's no trees. And it's like, no, that doesn't seem right. It's somehow inverted. It's very hilly, but rather than the hills rising up from the horizon, you're on top of the hills, and the ravines are cut down, below you. So it's just very peculiar.
Well, that's where the question always starts: is why is it this way? Why is there a hill there? Why is there why is there a ravine, and how long has it been there? So we're going to start with the geology news, and Andrew will bring it to us, and anyone else who has any news items they want to throw into the mix. Then we'll move to show and tell that Sheila will lead, and Sheila's got a presentation for us on sort of basic mineral identification that'll help with show and tell. And then we have sort of a hard out at 1:30. We'll turn off the recording, but we don't close the room until 2, so people can hang out. And if you have any sort of residual questions of the nature of the sort that Tater just asked, about specific areas, we've got experts here. So feel free to stick around and ask your questions. Andrew, did I make you a co-host already? And are you ready to share your screen?
Yes, and yes.
All right. Andrew, did you told us a little bit about yourself before you started? Or am I asking you to repeat something you already said?
Yeah, well, no reason I can't do that again. My name is Andrew Dunning. I am a graduate student at Portland State University. I study active tectonics under Ashley Strag, who is an occasional lecturer here at GSOC. I'm particularly studying an area out in the Strawberry Mountains, and my thesis work is, I may add, dependent on Dogami and its associated data. I'm working closely with a couple of Dogami geologists, so it's important that they stick around at least for the duration of my thesis work. All right, I'm going to jump into the geology news now. This is a segment I've been producing monthly here for these meetings for the last 6 or 7 months, I believe now.
Yeah.
And compared to October and November, we've had a pretty eventful month so far. A lot of new research has been presented because we just finished up with the American Geophysical Union's annual meeting, which was virtual this year for the first time, which wrapped up a couple of days ago. I did not get a chance to attend any of it, but some people I know did, and a lot of them had a very good time. I'm going to start with the unpleasant news to get it out of the way. Once again, climate change is rearing its ugly head, and November 2020 is the hottest November ever recorded. 0.8 degrees Celsius above the 1981 to 2010 average, surpassing both 2016 and 2019, which were the hottest previous Novembers. We're on track to have a pretty warm winter across the globe, though because of the current La Nina cycle, which is going through the Southern Pacific, we anticipate a colder and wetter winter in the Northwest. But in California and throughout most of the southern United States, it's going to be hot and dry comparatively. And the world's largest iceberg has been drifting towards South Georgia Island in the Atlantic Ocean, Antarctic Ocean, not the Atlantic, although I suppose it's south of the Atlantic. This iceberg broke off of the Larsen C ice shelf in eastern Antarctica in 2017, and it's been floating around ever since. It's 130 kilometers long, 32,000 square kilometers. You can see South Georgia Island here in the picture. It's quite a large island, and the iceberg is almost as large again as the island itself. There's been considerable unrest in the Antarctic ecological community about what impacts this could have on wildlife. However, it seems that the iceberg has already grounded itself on the continental coastal shelf around South Georgia Island. And this was published about Thursday night. The corner of this iceberg broke off, suggesting that it could have already grounded itself. The iceberg probably juts about 600 feet down into the ocean because it's such a huge mass of ice, and it floats just like that. It's really deep into the water, and it could already be grounded, so it might not end up crashing into the island after all. And I'm going to move on to earthquakes now, which is a personal favorite topic of mine. It was a good month for earthquakes. We had a largest event was in Alaska once again, a magnitude 6.4, probably another aftershock from the July 28th this summer, is a magnitude 7.8, which was a very large earthquake here in the central Aleutians. There's been a number of large aftershocks as a result of that. There was a 6.4 off Russia right here, and a 6.1 here off China, and then two more down here in Chile. There were no major damage or casualties were reported from these earthquakes, which is what we always like to hear. There was a widely felt magnitude 4.4 in Hawaii on the flanks of Mauna Kea, probably not related to volcanic activity. It's pretty deep down. And I'm going to point out these ones in California just because I think there's an interesting tectonic thing going on down there that I think a lot of people up here in Oregon maybe don't know about. There was an earthquake up here north of the Bay Area, north of Clear Lake. This is a magnitude 4.4. Which is a very common earthquake size for this part of California, very seismically active area. But these two down here are both magnitude 3.6. They happened just a few days apart. They're probably not related. Earthquakes of this size are very common and more or less random in their occurrence interval. But they occurred very close to the Elsinore Fault, which is right here, one of the larger faults in Southern California. You've got the San Andreas Fault up here, which everybody knows about. Next to it is the San Jacinto Fault. So you got these three sort of parallel major fault structures down here in Southern California. And these two 3.6s are actually on an alternate strand of the Elsinore Fault, which cuts right through here. And so there's this dog leg in the San Andreas Fault right here where the main fault strand collides with the San Gorgonio Mountains, which is a Proterozoic Archean craton, very cold, dense, very hard continental block right here, part of the Mojave block. And so the San Andreas builds up a lot of strain right here. This is usually about as far south as the last two major San Andreas earthquakes have ruptured. And so this is a very high concern area of the San Andreas for future major earthquakes is really south of here. But this dogleg here causes the strain to accumulate on these parallel fault structures here. And in someday, millions of years in the future, the San Andreas main trace will jump over to the San Jacinto fault line. And then after that, further onto the Elsinore fault line, probably. So these small shallow earthquakes in this area are very common, this part of Southern California, really from the Elsinore Fault to the San Andreas is one of the most highly seismic active areas in the world. A lot of earthquakes happening here, most of them very small. We're going to move on to volcanoes now. We got a lot of volcanoes going on. There are currently 19 volcanoes with eruptions or ongoing activity in the month of December. And for the first time in 35 years, there are no Alaskan volcanoes erupting. I believe Pavlov was the last one that had a couple of ash puffs in November and since then has been quiet. So first time in 35 years that no Alaskan volcanoes are erupting. Probably won't last too long though. There's an interesting activity on Hawaii. Obviously, there's no ongoing eruptions right now on the island of Hawaii, but a small magma intrusion was detected right in this area, just in the Kilauea caldera. There was an earthquake swarm around the summit of Kilauea in the caldera, and this is resulting from fracturing. Magma is intruding as a dike underground, so you get this small body of magma forcing its way up through the volcano body and inflating the summit. You can see these green arrows here. These are from tilt meters, which show which way the mountain is expanding and kind of deforming as a result of magma that's forcing its way up. These intrusions do happen pretty frequently, but they don't always result in eruptions. Pretty small. The USGS said that the volume of magma that intruded here is equivalent to about 1 hour's worth from the Fissure 8 eruption about 2 years ago now, if you remember that. That's the end of my volcano news. I'm going to jump into some new research that was published. Some of this is kind of technical. I've done my best to distill it a little bit, but if you got questions, interrupt me. Go ahead. This is one that I really liked, having just finished my tectonic geomorphology class, which Patty was in as well. And this is about erosion rates in the Alps and how those can be determined to discern uplift. The Central Alps have long been thought to be fairly stable in their uplift. They thought that they weren't really uplifting much anymore. It's a convergent margin. There is a subduction zone under Southern Europe, which is uplifting the Alps. And we call this dynamic equilibrium, where the erosion rate and the uplift rate are staying about the same. And so the surface of the land isn't moving too much. However, they used, these researchers, De Lunel et al., they just presented at AGU also, I believe. They used beryllium-10, I forgot to superscript the 10 there, which is an isotope of beryllium. It's a result of cosmic rays colliding with oxygen, usually in quartz, and this is called cosmogenic surface dating, and we use this to figure out how long a rock has been exposed to the surface. And through their analysis, they determined that the Central Alps, mostly around here, are uplifting at about 80 centimeters per 1,000 years, which is a pretty good clip for uplift in Central Europe. There are some areas where erosion is exceeding uplift, and those are these red dots, but everywhere else, especially with these little blue ones, uplift is far exceeding erosion. And one of the reasons the authors suggested in their discussion was that tectonic uplift is being augmented by glacial rebound. The Alps were, in the last ice age, and up until fairly recently, a heavily glaciated mountain range, but in the last 100 years, a large volume of that ice has gone, especially since the last ice age, and the weight of that ice being removed causes the crust literally to bounce up. It's a kind of a buoyancy. We call it isostasy in geology, how the buoyancy of the crust interacts with the mantle below. And so the uplift, the rebound of the crust resulting from the weight of the glaciers being removed could be a driving force in this rapid uplift.
Is it appropriate to put in a personal item here?
If you like.
My parents, I mentioned they were exploration geologists. One of the things they explored for was beryllium.
Oh, cool.
They used an antimony 124 radioactive that put out a gamma ray and caused the beryllium to put out betas, which they detected.
Oh, very cool.
We had a lead-lined box with the antimony in our basement, and they had a big wooden structure with my mother on one end and my father on the other end when they were carrying it around. So it was the first portable barrelometer. Previously, they had to collect the stuff and take it into some place to be assayed.
That's very cool. I didn't know about that.
So this isn't the only way that beryllium is active to being exposed to things.
Certainly. There's a An interesting paper that has been, oh, did I hear a comment? Nope. Interesting new paper suggestion has been put forward for volcanoes in the Aleutian Islands off of Alaska. They have proposed that these 6 Alaskan volcanoes, including Cleveland, which is this one here, the most active volcano in North America, could be part of a linked volcanic system, and which, you know, that's very common. There are large volcanic systems in the world. Lassen, Three Sisters, these are very large volcanic systems. They're proposing, however, that this is the result of a Yellowstone-style caldera, is their volcanic model they're proposing. And they're suggesting that the bathymetry and the geometry, the topography suggest this, as long as the presence of a large volcanic tuff unit with an unknown source does come from this area. There's a very good article on Smithsonian that kind of went into some of the finer details of their this proposal and their research. The ultimate thing is that it doesn't require a massive caldera for this system, but it's an interesting thing nonetheless. And the authors themselves have stated that much more research is going to be needed before they can certify this. And obviously it's a very remote area. Most of the rocks are not only underwater, but in Alaska. So it's a hard area to get to and find out more about. And something close to my heart is a new paper that was put out about lava tubes. I love lava tubes, any sort of volcanic cave. I love a good hole in the ground. And my favorite lava tubes are ones that contain ice. This is pretty common even now in this warmer climate we're living in now. But the ice that's found in these lava tubes was likely used thousands of years ago by ancestral Pueblo peoples and other Native Americans throughout the West. The large amounts of ice that you find in some of these lava tubes were probably used as a water source in dry periods. So certain lava tube geometries, a lava tube is a cave left behind in a lava flow. Lava flow forms, sometimes there'll be a little insulated area in the middle, lava drains out, leaves behind a void. And certain geometries of these caves trap cold winter air and form large blocks of ice underground. We got a lot of these in Oregon. And these chunks of ice, because they form seasonally, are very valuable records of paleoclimate, sometimes going back thousands of years. And researchers getting ice cores out of this cave in New Mexico in El Malpais National Monument, they found charcoal under down deep under the ice. And since this was far enough away from a cave entrance that they ruled out it was brought in from surface, they determined, along with some anthropologists they contacted, that this is very likely evidence of humans with wooden torches going down into the cave to get ice for their water source. And they used carbon dating to date the charcoal they found in this ice, and it correlated very nicely with a drought. I believe it was 940 AD around about. And this drought is known from tree rings. It's called dendrochronology. Close tree rings over a year show that it was a very dry season. And there was a long drought around then that we know from these tree rings, and the carbon dates of this charcoal correlated with that nicely, suggesting that in this time of prolonged drought, ancient Pueblo peoples ventured deep into this cave to retrieve some ice to melt for their water source. If you happen to be a fan of lava caves like me, or you want to learn more about them, I have a video all about an Oregon ice cave at my YouTube channel. URL is there and in the chat below. And to round this off, is that, yep, oh, oopsie. To round this off, I'm going to talk about a very remarkable thing, the highest ice cores ever retrieved. These researchers mounted an expedition to Mount Everest late last year to collect ice cores for their climate research. They got analyzed this year and their findings were presented at AGU last week. These are the highest ice cores ever received, and it's really interesting that they were able to, produce and analyze such high quality, very well preserved ice and climate data from the Himalayas, from the roof of the world. And they used a relatively new method for this. I mean, it's been done for a while, but it's really getting better and better every year. It's called laser ablation. And they take the ice core and they use a laser to go every few tenths of a millimeter all the way for the length of the ice core. And they used to do it by taking a little piece out of the ice and melting it. But now, I mean, that's we can have much higher resolution, seasonal, really even level data from these ice cores by using this laser. And it's revealing seasonal changes and climate change in the Himalayas, which is an important area. And the Himalaya do provide a water source for billions of people across Southeast Asia. And that's rounding out the geology news for this December of 2020. I didn't get into any of the AGU stuff because I wasn't there, but I've heard it was quite successful. There's lots of it written about it on the internet if you're interested.
That's wonderful. Any questions for Andrew?
So Andrew, there's a question from Bill in the chat. He says, concerning the uplift in the Alps, how can you differentiate between isostatic rebound, uplift and uplift caused by tectonic compression?
There's a number of ways. I don't know about any, this was just a thing that they mentioned. It was really very minimal, their discussion of this. We are able to determine using GPS and sort of some other satellite-based remote sensing methods, because Italy down here in Europe are moving at roughly the same rate from year to year for the last tens of thousands, hundreds of thousands of years. But if it is isostatic uplift, it's going to be moving faster now than it was then, the uplift-wise anyway. I'm sure Sheila and or Clark could talk about this in more depth than I can.
Sheila there?
Yeah, I'm
Okay.
here.
All right. We're almost at our hour. Sheila, are you ready to go? I have another question for Andrew.
Yeah, go ahead.
Okay. So I have my Google search set to give me updates whenever there's a new paper about geology. And so I'm going to put you on the spot because you probably didn't have a chance to digest this entire wonderful paper by William Lehman about cascade subduction zone volcanics. I barely got through it and I had to skip over a lot. Do you feel like you could describe it at all, or at least give us a sort of thumbnail description of what the issue is?
Yes, let me pull it up here. Wait, which you sent me?
I sent you two. The one that we were really interested in is the one that concerns the boring volcanics.
I didn't get that one from you.
Okay, well, you got the other one on tectonics?
I've got the tectonic one.
If you want to talk about that, you can talk about that. We can come back to the Lehman article next month because that's a lot to digest.
Yeah, please send that to me. I didn't see that.
The Lehman article I'll describe very quickly it describes the question that we've had about where these boring volcanics like Mount Tabor and Mount Scott are coming from, because they're happening in the forearc, and that's not usually where you get volcanics. You get volcanics where the subduction zone has gone down to the crust has gone down to a certain level, and Scott and Sheila can correct me on this, and then you get the cascades. But here we have these volcanoes in the metro area like Mount Scott and Rocky Butte and so forth. And it's kind of a geological mystery. I think to summarize, and maybe Andrew, you can come back with a better summary next month. It's complicated and it's a lot more complicated than it looks. The thing that's fascinating about the paper is it looks like it's a lifetime of work understanding the complexities of various subduction zones. So that kind of whet my appetite, but again, it was pretty technical. So I hope that someone like Andrew can kind of digest it for us.
Paul, can you paste the link into the chat?
I will do that. I will do that. Any other questions about geology news or any news that's floating out there that people would like to discuss? And then Sheila's going to give us a nice presentation about mineral identification. And I think she has an assistant today.
I do. Autumn. She's coming.
All right.
Come on. Are you ready
Andrew.
for this? Okay. Yes. I have an assistant here, my wonderful granddaughter, and this is Autumn. Say hi, Autumn.
Hello.
And Autumn is my oldest grandchild. She's older than her brother by 4 minutes.
No, by 1 minute.
1 minute. 1 minute. They're twins. So anyway, she's going to be here to help me today. And Autumn, would you like to just say a couple words about why you got interested in minerals and rocks? Because she loves minerals and rocks.
And last year in 4th grade, I had a really good teacher named Missy Chari, and she got me really interested in rocks. The way she taught got you engaged, and she was really fun. and I found out that I really liked rocks and learning about volcanoes and minerals.
Good, very good. And just to know, Mrs. Achari and I have been good friends for many years. And we actually started college together. And we took Bill Orr's class in mineralogy. So I just, that's what got me interested to go on. But it's kind of neat that she's now a fourth grade teacher and she's teaching young people to love geology. So it's great. And it's great to have Autumn with me today. And let's get started then. Or do you want to take a break here?
Sorry. No, why don't you go ahead? We have 3 people who have contributed to the show and tell. So we want to try to get that. We've got a half hour, which is perfect. So yes, we'd love to hear your presentation.
Okay. Well, let me change. Yeah.
Real quick, maybe it's just a good time to point out that Bill Orr is going to be with us on this meeting next month.
I forgot. That's
Yeah,
right.
Bill Orr
Thank
is
you.
going to come and identify fossils. So especially if I can't identify the fossil, he can. He's the one I always lean on for fossils. So, because I think there's a fossil in the show and tell, I think is what you said.
There is. Jeff Lee had a fossil in the show and tell, and I don't see Jeff at the moment. He might want to have it hold over until Bill can take a look at it, but we'll see how we're doing on time.
Yeah, we'll see how things. Okay, so let me change over to my document camera here so I can put some things under there, and let's see how this goes. I'm going to be teaching a class on rocks and minerals for Shemeketa next term. And so this is kind of a trial run on how we're going to do this in the remote setting. So thanks for, so I have my document camera here and I have specimens set up and that I want to share with you. Okay. So, and your turn will be in just a minute. Okay. Okay, so what I want to do is, a lot of people always ask me, how do I identify minerals and how are they identified? Well, I'm going to set out a bunch of minerals here. Hopefully you can see color here. Got a beautiful blue one. I've got some rose quartz, red, okay, or pink. I have a beautiful green here. Okay. I have a variety of different minerals.
Sheila, can you share your screen so that we can see the bigger picture of them?
No, this is a document camera. It's not, and it wouldn't help to share the screen. What does help is go up to your upper right-hand corner.
Actually, I've just spotlighted it for everyone. So did it get spotlighted for people?
Yes.
Okay.
Are you seeing the bigger, don't put your Zoom setting on gallery view so that you see all the people, but put it on speaker view, and then my screen will be much bigger. Is that what we're seeing here?
Yeah, it's good now.
Oh, okay. Okay.
That's great.
Okay, so hopefully the color comes through. We kind of played with the lighting a little, but here you've got, okay, so I've got 3 different minerals. I have a fluorite here that is green. I have calcite here that is blue, and I have quartz here that is pink. So color, is that the best way to identify minerals? Well, it's certainly the first thing that we notice, okay? Can't deny that we notice it. But here we got a problem. Here, I've got a green calcite. Let me show you the color, see if the color comes through, okay? Hopefully that shine that you see, we call that luster, and it's picking up, it kind of getting in the way of seeing the color. Okay, I've got some apatite here, which is also green, okay? And I've got some this is fluoride, calcite. What else did I have that was green? Well, anyway, I have green minerals here. Okay, so color isn't the best way to identify them because we can have several different minerals be the same color, or we can have a variety of minerals. We can have something like fluorite. I've got a piece of fluorite here that's purple. Okay, so and probably quartz can also be purple. I've got a nice quartz crystals here, part of a geode. This is amethyst. We call the purple stuff amethyst. Okay, so color is the first thing that you see, but we need to use other mineral properties to identify them because there are so many different ways that color can manifest in so many different minerals. So one way that we do it is by cleavage. Okay, cleavage is how a mineral breaks. So I've got this nice piece of calcite here, and it's demonstrated here. I've got a clear piece of calcite. What do you notice about the two of them? About the same shape. Okay, it's got what we call perfect cleavage in 3 directions. So top and bottom is one direction. This is another direction. Each dimension is a direction. Okay, so height, width, and length. And in all three directions, this mineral breaks perfectly into these little parallelograms. And the angle between them is, we've got an acute angle here and a larger angle here. So in other words, nothing's in right angles. Okay, so that's how we identify calcite. This what we call rhombohedral cleavage. I've got a piece of fluorite here. And I don't know if you can see these lines through it. I'm trying to show you how we see these lines through it that give you a hint to how it would break. I've got a big chunk of fluorite right here. And you can see kind of a line, diagonal line through here, some diagonal lines. This gives you a hint of what the cleavage would be. If you hit it just right, you can get it to break into these little diamond shapes. So let me show you an example of a cleavage fragment that's been worked by people. Now, nobody cut this, and nobody shaved it off into this perfect little diamond shape. Okay, it's just there because of the natural cleavage. If you tap it with a hammer just right, you can get it to break along the lines of cleavage. Cleavage in any mineral is the bond between the atoms that can break. It's got zones of weakness in there, and because all minerals are made of repeating patterns of atoms in a definite pattern, then there's zones of definite weakness through there. And so when you tap it that way, tap it a certain way, depending on the cleavage of the specific mineral, you're going to get this shape. Okay, so cleavage is a good way to identify minerals, or it's one way to identify it. Take, for example, this. And when I was putting together, I got this piece, and this piece I thought at first was fluorite because it comes in, notice you can see 2 colors. You can see green and I can see purple here, 2 colors within the same specimen. Fluorite can do that. But then I started looking at this a little closer and I thought, wait a minute, look at the cleavage. You see that rhombohedral cleavage here? Okay. And so that kind of tipped me off that it's not fluorite. Here I've got a piece of fluorite that's got 2 different colors in the same specimen, a little hard to see. Maybe you're getting a glint of the purple here, and then another glint of the green part here. So 2 different colors in the same specimen. So I got to thinking though, look at that cleavage. And then I do something else. I can test the hardness. I'm going to show you here. I'm going to scratch this, and I've got with me a steel instrument, which has a hardness of about 5.5. I'm going to scratch the calcite right here. And you see, I put a scratch in it easily with something of a known hardness. This has a hardness of about 5.5. Okay. I'm going to, the ultimate test to see if it's calcite is calcite reacts with hydrochloric acid. Okay, so I'm going to do the ultimate test here and put a drop of hydrochloric acid on it. Do you see it fizzing? Okay, that pins it down exactly that it is calcite. Okay, I didn't bring anything in to wipe off this. I'll wipe it off here. We don't want it marring my piece. Okay, so we use this is the definitive test, is the acid, but there's other tests that can be done. If you don't always have an acid with you, you probably have a pocket knife with you, and you can see if you can scratch it. Okay, if I have something like quartz, and I've got a quartz crystal right here, okay, and I try to scratch it with, I can't scratch it, okay, because quartz has a hardness of 7. And that's harder than the 5.5 of the steel. Okay, calcite has a hardness of 3. Fluorite has a hardness of 4. Here I've got a nice piece of green fluorite. And as you can see here, maybe put a scratch in it. I don't know if you can see the scratch I made or not. Right there, I'm pointing to it. Okay, I made a scratch in it. Okay, so hardness is really one of the better ways to identify a mineral. Okay, I've got some mineral specimens here. Let's see. Did you take some? Okay. Oh, Autumn is going to do a little test for you. So put it under here, Autumn. Okay. And she's got a piece of
Fool's gold.
fool's gold, fluorite. How do you tell that from real gold?
Well, we would be rich.
We would be filthy rich if we had a chunk of gold this big, wouldn't we? Okay, but so how are we going to tell? She's going to streak it on a streak plate. A streak plate is just a piece of unglazed porcelain. And then she's going to make, and we're going to look at the color of that streak. So go ahead and streak it. What color did that come out?
Gray, like a pencil.
Gray, very much like a pencil, because it's a sulfide mineral, and all sulfide minerals streak in black. Okay, good. So thank you for helping me. Did you get some other, let's see, we've got some other pieces here. We have some clear pieces. So streak is, thank you, Autumn, for helping. Streak is another way that we can identify minerals then. So the color of the streak tells us that this is not real gold, that this is fool's gold. Okay, one way you can tell. Okay, let's look over here, and I've got 3, let's go back to hardness for a minute, and I've got 3 different minerals. They're all clear, so you're seeing the black background coming through them, but they have 3 different hardnesses. And so hardness is defined as scratchability. Okay, if you didn't get that. So it's not how hard it is, like if I try to break it with a hammer. It means, does it resist scratching or not? Okay, so my steel here has a hardness of 5.5. So I can easily scratch gypsum. I've got some selenite gypsum here, and it easily scratches. I can scratch calcite. I don't know if you saw a couple, see little two little parallel lines there. And then I cannot scratch the quartz. I've got 3 different clear minerals here. And so I can't, so we compare hardness. Now, my fingernail and your fingernail is a hardness of 2.5. So the gypsum's only a hardness of 2, so I can scratch this with my fingernail. I'm putting a nice scratch in there. Okay, and you can see that I can easily scratch it with my fingernail, but the calcite, which is a hardness of 3, is just a little bit harder than my fingernail, and try as I can, I cannot scratch it. And then the quartz is a hardness of 7, so there's no way I'm going to scratch it with my fingernail. Okay, I take a piece of glass here, and a glass has a hardness of about 6.5, depending on, about 6.5, depending on the formula that the glass was made of. And you can see that there's already some scratches here because I've used it for other things. But if I take something very soft, like like my gypsum, I can't scratch it at all. Okay, I take the calcite and I can't scratch the glass. And the way that you're going to tell is not that if you see the scratch, because there's already previous scratches in here, but you're going to feel it. If it scratches, it makes a scrunchy kind of sound. So quartz is going to scratch the glass. I think you can see the scratch here. If you're seeing what I'm seeing, I hope you're seeing what I'm seeing.
We're hearing the scrunchy sound.
Did you hear the scrunchy
Yeah, we
sound?
heard it. Yeah.
Okay, I'm going to do it again. So listen for the scrunch.
Oh, it's like fingernails on a,
Yes, exactly.
well, it's not
And
like fingernails on a chalkboard, is it? It's like
Uh,
quartz on glass.
It's quartz on glass. And so, if you're using a piece of glass in a classroom that's everybody else is scratched, you might not tell if you're scratching it, but you can certainly tell by the scrunchy sound. Okay, so hardness is really one of the best ways to identify minerals.
So we did have a question. We have
Yeah.
the question that
Okay.
everyone should, probably needs to be asked every time. Patty asks, what's the definition of a mineral?
Okay, the definition of a mineral is a 5-fold definition. So first of all, it has to be a solid, okay, not a liquid. It has to be inorganic, meaning not part of a living thing and never once part of a living thing. It has to be, it has to have a distinct, it has to have the minerals, the atoms have to be arranged in a repeating crystalline pattern, which is a repeating structure. If you could look at the atoms, they're in perfect order, okay? And it has to have a certain composition, meaning that all silica is SiO2, 2 silicon to 1 silicon to 2 oxygen. It has to have that formula, that specific formula. Calcite is calcium carbonate, CaCO3. So 1 calcium, 1 carbon, and 3 oxygen. That's the formula for it. And all minerals have a specific formula.
And Sheila, would ice be a mineral?
Ice is inorganic if it's natural from Iceland or from Antarctica. Does it have a specific composition? H2O. Okay. Are the atoms arranged in a repeating pattern? Yes, that's why ice expands. Ice has a way of putting its small atoms in a repeating pattern, and that's why ice expands when it freezes. So yeah, ice is technically a mineral.
How about obsidian?
Obsidian. Okay, there's obsidian is glass, and glass isn't a mineral. Why? A couple ways. If it's man-made glass, it's certainly not. Okay, because minerals have to be inorganic and not man-made. Okay, so if it's man-made and it looks like a mineral, like I got some beautiful pieces of glass over here, given to me by a wonderful 4th grade student. Okay, and they look beautiful and they look crystally and everything, but it's not a mineral because 1, it's man-made, but the other reason is the atoms are not arranged in glass in a crystalline pattern. They're arranged randomly, like like water is when it's melted, you know, when ice is melted and water, the atoms can flow over each other. So actually glass is kind of a very thick liquid. Did you know that? If you have
I
a
suspected
piece
it. That, I wasn't absolutely sure that it wasn't going to be a mineral, but I wondered, given that your definition, whether it would classify.
it violates two of
Two
the
of the-
qualifications to be a
Okay.
mineral. It's man-made and it has no crystalline structure.
I was thinking about obsidian, but
Yeah. Okay.
so
And then
we
one
have
other
about 10
cool-
minutes left. So that's, and we have two.
Okay, that'll be just enough time to show me
Well,
my
Sheila,
last.
Sheila, we want to go to the show and tell.
Okay, but let me just do this one thing. One other
Oh, yeah, you
cool
gotta do
thing
this.
about calcite is that it has a property we call double refraction, meaning that you can see through it. When you look through it, you see double. So I put a little happy face on a piece of paper here, and you can see it. And then if you look at it through the calcite, you see a double image. Hey, everybody see a double image there?
We do.
Okay, so so calcite has that property of double refraction. Now a double martini will do that too. Okay, okay. So that's what I have for you. I'm going to change back to the regular camera.
All right, thank you. I hope you can come back next month and give us another intro geology lesson. I think it's very helpful, even for people who have been in the club for many years. I mean, that's still, some of that is information that's either new to me or I need to be reminded of.
Okay.
I'm sharing the screen now, and this was one of the first things that came in. Now, Jeff Lee submitted some fossils. I don't see him at the moment online, and so I'm gonna ask, well, we'll put his fossils over till next month when we have Bill Orr, the expert himself, to look at them. But let's start. Whose cobble is this? If she could unmute and tell us. I know she told us in the social.
Chris Lazarus. So yeah,
Okay.
I found this, suddenly it appeared on our street. So
Oh, it
right.
appeared on your street. Where are you living?
St. John's in Portland.
Okay, okay, good. Well, you know, it's really hard to identify things in the online environment, but I have a feeling, let's go back to that first picture that you're showing.
Okay. I'm gonna blow it up a little bit.
Okay, one thing is you labeled it as a mysterious pale rock because it's pale. And that's a very good observation there, that most of the native rocks in this part of Oregon are basalt, and they're black and they're dark. So this one is mysterious to you because it is a pale color. Now, I also see that it's nice and rounded, which tells me that it's been down a river and looks like a river. And I'm thinking the size of this is maybe about the size of my hand, just guessing. Don't have any, you know, maybe looking at the concrete below it, which is beautiful, by the way. Lots of nice little pebbles.
We could talk about the concrete too.
Yeah, we could talk about the concrete.
Maybe another time.
Made of calcite, okay, and then they put aggregate in there to all the little pieces of rock. But anyway, I think that this is a, so we would call this size a cobble, okay, about this size. And without breaking it in half, the only way to know for sure what it is to break it and get a fresh piece of it. But my suspicion is that this is quartzite.
Ah, okay.
Now, quartzite is a metamorphic rock made from smushed, you like that term, smushed. Heated and pressurized sandstone. And let's go back to what sandstone is. Sandstone's made of sand, but what is most sand? Most sand is made out of quartz. Okay, little quartz fragments of quartz, because quartz is the last thing to decompose when rocks decompose. And so it's the most stable at Earth's surface temperature. So by the time you get down to the beach, unless it's an unusual thing like a coral beach or even an olivine beach, those are unusual, the green sand beaches. But most beach sand is quartz. Okay, so that's going to end up making a sandstone. And then the sandstone came under heat and pressure to become quartzite. Okay, so now what is interesting about this is that you recognize that it's mysterious, that it's non-native. In other words, it doesn't look like all the other rocks around here. But remember, I told you earlier that a river is an inventory of everything that's upstream from that river. So this is telling me the presence of quartzite is telling me that this came originally out of the Columbia River and not any of our local rivers. Okay, so we have a place, we have the Troutdale Formation in Troutdale, and we have the Sandy River running through there, and it exposes a really nice pebbles on the side that the Troutdale Formation is made of cobbles that are, you know, what we call a conglomerate. It's got big pieces of rounded rock in there. And the natural supposition, you know, since it's next to the Sandy River, is that it came from the Sandy River. But when you look in it and you see those pieces of quartzite, the Sandy River, where does it come from? It comes from Mount Hood, okay, which is all igneous rock. So the presence of quartzite tells you that this had to be a place that had metamorphic conditions going on, like the Rocky Mountains. Okay, because we only have 2 places in Oregon that are old enough to have metamorphic rocks, and that would be the Blue Mountains in Oregon and the Klamath Mountains. Well, in the source of the Columbia River is in the Rocky Mountains or you know, mountainous areas where there's been metamorphism going on. So it took the sandstone, turned it into quartzite, and then this has now rolled down the river, gotten into the Portland area, and you got a hold of it.
Great, thank you. That's so interesting. I'm going to give it to the friend who found it with me, lives in Seattle area, and her son is interested in rocks. So I'm going to give it to him. It's going to wind up in Seattle.
Now, if you were brave enough to break it a little, you know, and it's very hard to break because it's very tightly metamorphosed, but if you could, or take another piece of quartzite and break a fresh piece and look at it with a hand lens. You know what a hand lens is? The little lens that a geologist puts up against their eye. And you can see almost magnified, like a, almost as good as having a microscope. But you'll be able to see the little quartz grains, the little sand grains, they're now fused together. A lot of times, if you look really closely at a piece of quartzite, you can still see the remnants of all the little sand grains that used to be, but they've been all kind of fused together by metamorphism.
Wow, great.
All right.
Yeah, very
Thank you for
fun.
submitting that. Well, we have 4 more minutes and we've got one, this is submitted by Kathy Moyd. So I guess the first question is always, well, I'll leave it to Sheila. What's the first question you always ask when someone brings in a rock or fossil for you?
Well, I wasn't bringing in for her. I already got my identification from the mineralogist I was with when I collected it.
Okay.
All right.
But I had to check Google to learn how to spell apophyllite.
Okay, so the first question I think we asked is, where did it come from? It came from Kathy, but where did you find it or where did you collect it?
Paterson, New Jersey.
Patterson, New Jersey.
And it's a location that's known for beautiful mineral specimens. But it's right in the middle of town. And so it got to the point where, you know, you couldn't go do any blasting and expose new stuff. But when a developer got permission to blast on the site, they took some of the minerals that had been collected there and showed it to him. And he agreed that he would do blasting on Fridays, but not clear until Mondays, and would notify the local mineral clubs And so I went down with the New York Mineral Club one day and got this specimen. And it was agreed it was the best specimen to come out of there that day.
So I think we have, and Sheila can comment on this, we see heulandite in this part of the country, and it's usually where, Sheila?
I'm not familiar with this at all.
I think it's a zeolite.
Oh, okay.
Yep, it is.
So where do we?
Okay, so a zeolite is something that forms kind of a secondary mineral that forms in, very often we have zeolites here in Oregon that form in cracks in basalt. They've been under the ocean, and then a crack develops, and the zeolite crystals grow inside of those cracks. Kind of a secondary. Where was this found in? Did you find it in this condition?
No, I found it, the heulandite was whole when I found it, but in the course of a number of moves or cleaning people, part of it broke off.
All right.
Okay, so what was it in was it enclosed in a different rock when you found it, or you just found it laying on the ground?
This is what I found.
Okay, so looks like it's okay. So I'm guessing here. So somebody else who's here, step in and help me here. I'm thinking the zeolites is this crystally stuff that you see around here. Are you seeing my pointer?
We're not seeing your pointer, but I have mine.
Okay. See that kind of, you've got this big crystal in the middle, but then you've got all this. Zeolites usually has a habit of, they're very fragile. They break off what we call a acicular habit, where the needle, it's a bunch of little needles.
You can look, you can check the cleavage.
All right.
Yeah.
Well, we're at our 1:30, so I'm going to stop there.
Okay.
We keep the room open for a half hour, so I'm not going to kick anyone out. I'm going to take a little break. People can chat a little bit. And thank you, Sheila, for a wonderful presentation. I think Carol has turned off the recording now. I will excise the part of the recording where people did their